Before we start the new lesson, I would like to ask you the questions. Is there a solution to equation square of x equal to 2? What shape do all points with a fixed distance to a fixed point form? Through discussion, we reached a consensus. The equation square of x is equal to 2 and has no solution within the range of rational numbers. In the range of real numbers, it has two roots, root 2 and negative root 2. A circle is formed by points that are equidistant from a fixed point in the same plane, and a sphere is formed in space. It seems that clarifying the research object and determining the research scope are the foundation of our study of mathematics. So how can we succinctly and accurately describe mathematical objects and research scope? Let's take a look at a few examples together. 1. All even numbers between 1 and 11. 2. All first-year high school students enrolled in Lyde Middle School this year. 3. The four major types on Earth. 4. The solution of inequality x minus 7 is less than 3. 5. Smaller numbers. In question 1, we take every even number between 1 and 11, namely 2, 4, 6, 8, and 10, as our research object. In the second question, every high school freshman who enrolled at Lyde Middle School this year is our research subject. How to express in mathematical language. In our elementary and junior high school learning process, the term set is not unfamiliar to us. We have studied natural number sets, and just now we mentioned that the set of points in the same plane that are equidistant from a fixed point by a fixed length is a circle. So we will use set language to describe our mathematical object and research scope. To better utilize set language, let's first take a look at the meanings of elements and sets. Generally, we collectively refer to the research object as elements, and the population composed of some elements is called a set. For a given set, its elements are deterministic, meaning that the elements of the set are deterministic. The elements of a set are different from each other, which means that the elements of a set have anisotropy. Set elements cannot be duplicated. As long as the elements of two sets are exactly the same, we say that the two sets are equal, which means that set elements have disorder. Okay, looking at examples 3, 4, and 5 mentioned earlier, can they form a set? What are the criteria for judgment? Just now we clarified the meanings of sets and elements, which means that set elements have determinacy, mutualism, and disorderliness. This is the standard for our judgment, and what we need is to think rationally about this issue. According to this standard, 3 and 4 can form a set, and smaller numbers of 5 cannot form a set. Its elements do not have certainty, such as tall classmates or swimming experts. We usually use uppercase letters A, B, and C to represent sets, and lowercase letters A, B, and C to represent elements. If A is an element of set A, we say that it belongs to set A, denoted as A belongs to A. Classmates, this is the first unfamiliar symbol we see in high school learning. We need to clarify its meaning and familiarize ourselves with its representation. If A is not an element of set A, we say that it does not belong to A, denoted as it does not belong to A. These two symbols are still very reasonable, similar to our concepts of equals and non-equals. We just mentioned that we can use uppercase letters to represent sets. So let me use it now. We use capital letters to represent every even number between 1 and 11 mentioned earlier. What is the relationship between 3 and 4 and set A? How can we express it in mathematical language? We can easily know that 4 is an element of set A, and 3 is not an element of set A, so we say that 4 belongs to A and 3 does not belong to A. We use mathematical language to record it very concisely. Some commonly used sets of numbers have been listed by our teacher with fixed techniques, such as the set composed of all non-negative integers, which is called the non-negative integer set, also known as the natural number set. We remember the set of all positive integers n, which is the set of positive integers. We record it as n stars or n positive. What is the difference between these two sets? 0 is a natural number in the set n. In our mathematical language just now, 0 belongs to n. Let's write it as. And since 0 is not in the set of positive integers, we say that 0 does not belong to star n, so we record it as. The set composed of all integers is called the integer set, denoted as z. The set composed of all rational numbers is called the rational number set, denoted as q. The set composed of all real numbers is called the real number set. Write it as r. Set theory was founded by German mathematician Cantor in the late 19th century. At that time, Cantor went beyond the limitations of sets of numbers and proposed the general concept of sets when solving mathematical problems involving infinite research. Set theory has been praised by many mathematicians and philosophers. Russell described it as perhaps the greatest work that can be boasted of in this era. The establishment process of set theory reflects the background and objective needs of the development of mathematics. The discovery and creation process of mathematics is full of the imagination, creativity, and indomitable spirit of mathematicians, demonstrating the enormous role of human rational thinking. Let's continue learning. Our collections were all expressed in natural language earlier. Besides that, what other ways can we express collections? Let's take a look at the example we mentioned earlier. The roots of equation the square of x is equal to 2. Since there are only two roots, root 2 and negative root 2, we can list them one by one, separated by commas in curly braces. Similarly, all even numbers between 1 and 11 have 2, 4, 6, 8, and 10, which we can also list one by one, separated by commas and opened in curly braces. In this way, we list all the elements in the set one by one and enclose them in curly braces to represent the method of the set, which is called enumeration. 1. An integer greater than 1 and less than 6. 2. Equation the square of x minus 9 equals 0, which is the set of all real roots. Let's first take a look at 1. The integers greater than 1 and less than 6 are 2, 3, 4, and 5. Let's list them one by one in curly braces. All real roots of equation x where subtracting 9 equals 0 have 3 and subtracting 3. We will also list them one by one in curly braces. Did you write it correctly? Learned how to represent sets using enumeration. I have a question for everyone. Do these two mathematical symbols have the same mathematical meaning? Let's first take a look at the first one, which represents the number 0. Let's take a look at the second one again. Firstly, it represents a set represented by enumeration. This collection only contains one element 0. Obviously, their mathematical meanings are different. If their mathematical meanings are different, what mathematical language can we use to express their relationship? According to our analysis just now, they are the relationship between elements and sets. So, elements and sets are connected by a belonging sign, which means that element 0 belongs to this set, which contains only one element 0. We remember that 0 belongs to a set consisting of one unit element 0. At this point, the problem arises again. Can we still use enumeration to represent the set of points in the plane that are equidistant from a fixed point by a fixed length, as well as the set of solutions where the inequality x minus 7 is less than 3 that we mentioned earlier? For example, let's take a look at the inequality where x minus 7 is less than 3, and the solution is x less than 10. However, there are countless real numbers that satisfy x less than 10, and we cannot express them using enumeration. When there are countless elements in a set, how do we represent it? Let's also take a look at this example, where the inequality x minus 7 is less than 3 in the solution set. At this point, we can use the common characteristics of the elements to represent them. Here, our research object is x, and the research scope is real numbers. Their common feature is that x is less than 10. That's how we express it. Firstly, draw a curly bracket separated by this vertical line. In front of the vertical line, our research object is x and the research scope is r. Its common feature is that x is less than 10. Let's abstract it. Generally, let it be a set, which is our research scope. We take all the elements x in set A that have a common property px, which is its common property, and this is the research object. Let's put it this way. First, draw a curly bracket with a vertical line separating it. The research object is x and the research scope is A. After the vertical line, we will write down its common features. This method is what we call descriptive representation of sets. Of course, sometimes we use colons or semicolons instead of vertical lines. You should recognize it. We know that the integer set z can be divided into odd and even sets. So how do we use descriptive methods to represent odd sets? We first determine that the research object is x and the research scope is the set of integers. So, if x can be written in the form of x equals 2k plus 1, k belongs to z, then dividing it by 2 is the remainder of 1, which is an odd number. Conversely, if it is an odd number, then the remainder of x divided by 2 is 1, and it can be expressed as x equals 2k plus 1, k belongs to z, which is a common feature of all odd numbers. We can use descriptive methods to express. First, draw a curly bracket and a vertical line. The research object is x, and the research scope is integers. Its common feature is that x equals 2k plus 1, and k belongs to z. Can you use descriptive methods to represent even sets? Our research subject is x, and the research scope is integers. If x can be written as x equals 2000, k belongs to the form of z, and it must be divisible by 2, making it an even number. On the contrary, if it is an even number and can be divided by 2, it can be written as x equals 2000, and k belongs to the form of z. So, x equals 2000, and k belongs to z, which is its common feature. We can describe it this way. Classmates, is your expression correct? Please continue to think about how we can use descriptive methods to represent rational numbers in class. Let's recall this lesson where we learned the meanings of elements and sets. The elements of a set have determinacy, mutualism, and disorderliness, as well as the relationship between elements and sets, and we have learned to use symbolic language to characterize a set. Among them, we learned the unfamiliar symbols of the first high school stage, belonging and not belonging. Collective knowledge is the foundation of modern mathematics and also the basis of high school learning. In this class, we have a lot of new concepts and symbols. Students need to clarify the meaning represented by symbols, familiarize themselves with the representation forms of different symbols, use them more frequently, and return to concepts more often to establish the relationship between symbols and mathematical objects.